Arizona State University's Project VELOS was designed to support NASA's extraterrestrial exploration efforts by offering a configurable, reliable, and scalable solution for exploring the permanently shadowed regions of the lunar surface. The Variable Exploratory Lunar Observation System is a multi-probe exploratory system that is capable of launching sensor probes over 100 meters into a permanently shadowed region. Each probe is equipped with a configurable suite of sensors designed to optimize data collection potential and to survive the harsh lunar environment. VELOS allows NASA to gather more data in and around the PSRs by providing a scalable solution to exploring unknown regions of the lunar surface. During this presentation, we will walk you through the VELOS project by reviewing the problem statement and project objective. You will see firsthand the design and development of VELOS's most innovative systems, followed by the testing and validation results that were the outcome of iterative designs. Finally, we will conclude our presentation and this project with our results and conclusions.
Little information is known about permanently shadowed regions, or PSRs. As a result, data collection in these areas is of the utmost importance in order to accurately understand the region and its potential resources. The challenge is to develop capabilities to explore and to operate in lunar PSRs, which have been designated as an extreme environment due to its ultra-cold temperatures, lack of sunlight, and unknown surface conditions. VELOS is an innovative approach for exploration in an unknown environment by providing a system that is reliable, versatile, and scalable. Its novel launcher mechanism allows for the design of probes with different sensor payloads and allows the science mission to choose where each payload should be deployed. The VELOS system will enable future science missions to the Moon and Mars by providing a low-cost exploration system that can reliably launch multiple types of sensor payloads for valuable data collection, which can be designed by scientists or by students to explore and enable the next crewed mission to the Moon.
I'm here to tell you about the Variable Exploratory Lunar Observation System, or VELOS for short, which is our solution for exploring permanently shaded regions of the Moon. The word VELOS is Greek for arrow, which is fitting for the long-range projectile nature of the system. VELOS is a multi-probe sensor system capable of collecting data from 4 distinct locations on the lunar surface up to 100 meters away from the lunar lander. VELOS accomplishes this by deploying 4 sensor probes with a spring-loaded launcher. The probes can collect data for up to 5 hours in the PSR and wirelessly transmit the data back to the launcher safely on the lander. Because the probes can be deployed in specific locations, they're able to establish a mesh network such that the furthest probe in the field can still communicate with the lander via a relay probe. This system is not only highly capable, but also highly extendable for other missions. The launch payload isn't limited to the current sensor payload, and the range isn't limited to 100 meters, as the launch springs can be upgraded for stiffer and longer springs if the mission and payload requires. The mesh network capabilities of the probes also presents an additional use case where VELOS could quickly deploy a long-distance, temporary mesh network to interact with other equipment in the field, such as rovers. Overall, VELOS is a highly capable and reliable launching platform that could give us access to the hardest-to-reach parts of the lunar surface.
The design and development of VELOS was split into 2 subsystems made up of the launcher and the probes. During development, each subsystem was further broken down into electrical systems, which included electronics and embedded software, and mechanical systems, which included actuators and structural components. To display the hard work of the team and the concept we're all so proud of, we also dedicated a small team of students to produce a virtual reality environment to clearly demonstrate the functionality and necessity of VELOS.
The probe electrical subsystem is made up of 2 printed circuit boards, a motherboard for data processing, and a daughter board for sensor data collection. The motherboard includes 2 microcontrollers, a battery management system, and USB interfaces. The motherboard also incorporates an inertial measurement unit for measuring internal temperature, acceleration, and orientation of the probe. Each component is soldered to a custom printed circuit board, or PCB, designed by the VELOS team. The board includes components on both the top and bottom to optimize for space. The top includes the Wi-Fi microcontroller in Block A, which is responsible for Wi-Fi communication and data transfer from the probe to the launcher. Also on top is the secondary microcontroller in Block B, which is responsible for data processing from the VELOS onboard sensors. This microcontroller transfers data to the Wi-Fi microcontroller to send back to the lander. Then beside the probe board is the sensor daughter board in Block C, which is used to sample data near the exterior of the probe. The probe motherboard was designed to include onboard sensors such as the inertial measurement unit shown in Block D, which was used to measure the internal temperature of the board for thermal control purposes, as well as acceleration during the launch and impact to quantify the shock on the board. The inertial measurement unit was also used to track the orientation of the board to determine the final resting position of the probe once it had landed. In addition, the motherboard includes a battery management system shown in Block E and F to regulate the power from battery during charging and discharging. Each probe includes a 15.2 watt-hour battery that is roughly 1.4 times the capacity of an iPhone 12 battery. This battery enables the probe to power not only the main motherboard, but also the daughter board, developed for data collection near the surface of the probe.
In order to collect data near the exterior of the probe, we've developed a small daughter board, which hosts the Inertial Measurement Unit, or IMU. This component is critical for data collection, as it's responsible for collecting accelerometer data, gyroscopic data, magnetometer data, and temperature data. We would use temperature data to understand variations in temperature in and around the PSR. We would use the accelerometer data to understand the initial impact of the probe, as well as physical surface conditions in and around the PSR. We would use the magnetometer to understand if any magnetic field surrounded the PSR. And we would use the gyroscope to understand the physical orientation of the probe. In order to access data off of the daughter board, we would use the serial communication bus I2C for its reliable and easy data transmission to the main motherboard. Once the motherboard has this information, we can relay it back to the lander via a Wi-Fi mesh network. The VELOS daughter board was designed to maximize each probe's capability to recover and extract data from the lunar surface.
When designing the probe, we identified the following requirements. The probe needed to survive the impact of launch, as well as the thermal environment characteristic of the PSR, in order to transmit data back to the launcher. Weight was also a significant factor, and we finalized on a design that was 0.35 kilograms. For the outer structural shell, machined aluminum was used to create two hemispheres, which were pocketed for weight reduction. The system is thermally and radiation protected using multi-layer insulation, with an inside layer here protecting the electronics and an additional outside layer with a beta cloth exterior to prevent damage to the insulative layers. Our thermal blankets were designed and manufactured by Aerothreads after communicating our requirements, and we finalized on a 10-layer blanket system that was assembled during testing. In order to properly mitigate shock when the probe impacts the lunar surface, we designed a system that separates the electronics from the outer shell. In between the electronics and the shell, an expanded carbon foam is used to absorb the energy of impact. To further protect the electronics, the motherboard is enclosed by a high-density polyethylene case, which was designed for its electrical insulation, temperature resistance, and radiation shielding characteristics. These systems were designed to ensure that the sensor package enclosed within the probe's aluminum shell is safely delivered to its destination. The VELOS probe was designed to enable multiple form factors in the same system. Preliminary design of a probe was completed to accommodate a small version of the LunaMap neutron spectrometer designed by ASU's Dr. Craig Hardgrove for the Artemis I mission. This new design still fits within the VELOS launcher, with additional room for the neutron spectrometer inside. Preliminary calculations were done to determine that the probe could provide enough power to the neutron spectrometer for 2 hours, enabling the sensor to determine the presence of putative water ice.
The electrical subsystems of the VELOS launcher include a controller circuit board, 2 actuator motors, and 4 spring release mechanisms. The controller circuit board is made up of 5 major subsystems located on both the top side and the bottom side of the circuit board. These subsystems include the main microcontroller, shown in block A, which controls the actuators and spring release mechanisms. The stepper motor controllers, shown in block B, which isolate and drive 2 high power actuators. The power MOSFETs, shown in block C, which activate the 4 spring release mechanisms. The communications microcontroller, shown in block D, which transmits data from the probes in the field and sends it to the main microcontroller via Wi-Fi. And lastly, the step-down converters, shown in block E, which efficiently reduces the input DC voltage from 28 volts to both 5 volts and 3.3 volts. The VELOS launcher uses 2 high-power stepper motors with gear reductions in order to accurately modify both the longitudinal and latitudinal direction of the turret. The spring release mechanism pulls nichrome wire towards a high-strength paracord. This paracord is used to compress and hold down the 4 launcher springs. When activated, the nichrome wire will instantly increase its temperature, getting red hot. This will allow the nichrome wire to quickly burn through the paracord and release the launch springs.
The VELOS launcher was designed and tested to launch the probe 16.5 meters on Earth. That's the equivalent to 100 meters on the lunar surface with reduced gravity. The launcher can adjust the probe trajectory by actuating its altitude and azimuth axes. The VELOS launcher has 4 launch tubes. Each launch tube launches a single probe into a different region of the lunar surface. VELOS is easily customizable. Larger springs can launch the payload further or launch different payloads altogether. The probe is launched with a compression spring. The spring is compressed with a special machine and held compressed with a high-strength, low-stretch paracord. The spring and paracord are housed inside the launch tubes. In the rear of the launch tubes, there's a hot wire cutter, which severs the paracord when the probe is ready to be launched. When the paracord is severed, the compressed spring is allowed to rapidly decompress and launch the probe into the hard-to-reach, permanently shadowed regions of the lunar surface. The paracord hot wire cutter release mechanism allows us to rapidly run numerous launches and testing. The spring pushes against a specially designed low-friction plunger, which is what makes contact with the probe during the ejection sequence. This low-friction plunger is a critical part of the launcher assembly, as it keeps the spring centered and prevents damage to the inside of the launch tubes. VELOS was designed for safety and reliability, from the ground crew to the mission reliability. The VELOS launcher is preloaded using a custom spring compression device that is designed to safely compress the spring prior to launch. Once compressed, the system is designed to enable maximum flight safety by incorporating safety caps that are held in place by pin puller mechanisms. The device is also designed such that the launch tubes can safely nest within the base, which provides an inherently redundant safety mechanism during flight. The system is also designed to incorporate pin puller safety locks on each actuator that will only be released once safely on the lunar surface. The VELOS system prioritizes mission reliability by reducing the number of actuators and mechanisms, and increases mission safety by building redundant safety systems to ensure mission success.
The communications aspect of the VELOS project decided to adopt the root and leaf node mesh networking system. In this system, we have leaf probes, which are our leaf nodes, and then we have the root node, which is the launcher. These leaf probes are able to transmit all of their data directly back to the launcher, or they can mesh hop their data between each other, with one leaf node finally sending all of the data back to the launcher. This is similar to the concept of cell towers. Cell towers don't have to wait on a connection directly back to the main tower in order to get all of its data finally sent to it. They can actually send their data to nearby cell towers, and a final cell tower can send all of the data collected back to the main tower. So in the sake of the VELOS project, let's say we have 2 probes near a launcher. Those probes can transmit their data directly to the launcher every 1 second. But say we have probes deep into PSR and they have no connection to the launcher. They can actually take their data, transmit it to a nearby probe, and that nearby probe can transmit all of their data back to the launcher. Now, something else can happen. These PSR probes, say they don't have a connection to a nearby probe. They can either, 1, save their data onto their drives and wait for a connection to reoccur to a nearby probe, or the launcher can strategically launch a 4th probe into the network and create a new link in the system. This new node in the network could be a new node for the PSR probes to finally be able to transmit their data to, and this probe can transmit the PSR data back to the launcher. All in all, this concept of mesh networking is a great way to maximize the number of opportunities for data transmission to occur, and it can reduce the amount of time it takes to finally get data from out in the field back to the launcher.
Overall, the design and development of VELOS meets all the design constraints set forth by NASA's Commercial Lunar Payload Service, or CLPS, lunar lander. The total system mass was 15.3 kilograms, but only 14.9 kilograms without the testing base. The system consumes 7.18 watts during average operation with peak consumption of 38.8 watts. The VELOS communication network is based on the IEEE 802.11n standard for CLPS compliance.
We decided to create an educational virtual reality application in order to provide an immersive walkthrough of Project VELOS. Because this mission would be unmanned and is intended to explore such treacherous landscapes, we figured what better way to represent our concept than a first-person experience right there on the moon. The application is built for the Oculus Quest virtual reality headset using Unity 3D's game engine and the XR Interaction Toolkit. We chose the Oculus Quest as a cost-effective solution that offers 6 degrees of freedom and the ability to run untethered from a computer. When it comes to development, Unity 3D provided us an efficient platform to collectively design the application remotely. We would like to share this experience with as many people as possible, so the application will be available to try for free online at sidequestvr.com. Now, I'd like to share some highlights of what you get to participate in while using the application. All of the assets that you see here, from the environment and 3D models to the interfaces and animations, were created by the team and I. When you first start, you're briefed by our narrator who will guide you throughout the experience. It begins with an explanation of the mission and a chance to experience the moon's low gravity, as we all dream of doing. From there, we are introduced to the lander, along with its payload, which includes the VELOS launcher and probes. Next, we get a chance to inspect the launcher and probes by rotating and expanding their parts to see what they are comprised of. Finally, we complete the mission by aiming and launching the probes into the permanently shaded region to collect data. At the very end, we even threw in a little Easter egg that lets you swing at some golf balls as a nod to the historic Apollo 14 mission.
All 3 probe vacuum tests were completed successfully with temperature data logged and retrieved over the duration of each test. The primary interest was the performance of the micro-electromechanical IMU and the lithium-ion pouch cell battery under vacuum conditions. Research from the Johnson Space Center suggests that unconstrained pouch cells expand under vacuum and can suffer performance losses. The probe electronics enclosure was therefore designed to provide a snug fit around the interelectronics as well as the battery, and a 1/16 inch sheet of plastic was inserted between the probe motherboard and the battery to provide extra support. Because of this enclosure design, the battery successfully passed all testing with only a 0.83% increase in thickness compared to a new cell, and no noticeable changes in performance were observed. The IMU also passed testing and was able to provide internal temperature data, which was useful for predicting how the probe might react under thermal conditions, as well as further vacuum tests. These vacuum tests serve as preliminary verification and indicate that the system can successfully operate in partial vacuum.
After the vacuum tests were conducted, temperature was included to test the performance of the probe assembly under drastic thermal changes. Stainless steel blocks were cooled with liquid nitrogen to act as heat sinks. Once cooled, the probe with the MLI installed was placed on those blocks within the chamber, and the system was immediately pulled to vacuum. In the graph shown, a noticeable pressure drop occurs when the turbomolecular pump is turned on once the roughing stage has been completed. In both tests, data was continuously recorded from both the probe and external temperature sensors. These preliminary tests determined the probe can maintain a 100 to 140 degree Celsius temperature gradient from the outside to the inside of the probe with just thermal insulation. This data was then used to validate thermal simulations under full PSR conditions.
After completing physical testing, the team worked to simulate the probe subsystem. For the thermal vacuum simulation, a model was made and compared to the physical tests. This was done in order to validate the accuracy of the model using temperatures measured during the physical thermal vacuum test. The temperature of the electronics over time that was outputted by the simulation was compared to the temperatures found during the physical tests and found to be accurate. Using this same model and adjusting the input conditions to that of a lunar environment, it was possible to extrapolate the lifespan of the probe. The video below shows the simulation results of the temperature distribution throughout the probe across a 3-hour span. In this simulation, we also tested the effects of a built-in electronic heater. This can be seen in the plot below, where the effects of this heater on the probe's lifespan are shown based on varying levels of heating. When running the heater at 2 watts, we expect the probe subsystem to be able to maintain an optimal operating temperature in the PSR lunar environment for 2 hours and 15 minutes and survive for approximately 5 hours. To test the probe for impact survivability, we ran multiple drop simulations. In these simulations, the worst case scenario was tested for. This scenario would be when the probe is launched up to 100 meters and collides with a solid object, such as a rock. The results of this can be seen in the video below. In this clip, the electronics casing found inside the probe can be seen to oscillate upon impact. This is represented by the blue line on the plot, which shows the acceleration of the electronics during the 500 microsecond impact. The orange arch line to the left in this plot represents the acceleration of the probe shell itself. These values were compared with the standard drop test results and showed the electronics should be safe upon impact. Additionally, through the simulation, we were able to confirm that under this worst case scenario, the solid shell of the probe will permanently deform as planned for by our design.
For communications testing, we had conducted 3 different tests. The first test was a mesh network test. We wanted to make sure that all of the probes and the launcher could transmit data on the same network, and we found that this was possible at a rate of 1 Hertz. The second test we conducted was a node reconnection test. We wanted to make sure that if a node was ever isolated, it could reintegrate back into the network and do so in a quick amount of time, which based on our projectile motion calculations means we have a window of opportunity of about 15.5 seconds or less to make this happen. According to our tests, on average it takes an isolated node to reconnect to our mesh network in 12 seconds. Our third and final test we conducted was a multi-hop mesh network test. We wanted to make sure that if data was being hopped between the different probes and then back to the launcher, that this could happen in under 15.5 seconds as well. On average, we found it takes data to transmit between the different probes and back to the launcher at 5 seconds. Overall, we've concluded that our mesh network is a fast and effective way to transmit data in the space environment.
For testing, the launcher was rigidly fixed to an 80 centimeter tall table to act as a stand-in for the lunar lander. We began testing with very small, light springs to test for system reliability and safety. Over the course of 22 launches, we iteratively increased the spring's stiffness and length in order to achieve our launch distance goal of 16.5 meters on Earth. We used external cameras to track the trajectory of the probe as it was launched. We also used sensors on board the probe to capture the acceleration of the probe as it impacts the surface during landing. In final testing, as seen in the video, we launched a 0.35 kilogram probe to the launch distance goal of 16.5 meters on Earth, which is equivalent to 100 meters on the moon with reduced gravity. In the video, the yellow tape marks the launch distance goal of 16.5 meters from the launcher base. In all, launcher testing was another welcome success, as this VELOS iteration met all of our design constraints and performance goals, and proved itself safe and reliable.
For additional verification, the launcher was also entered into the vacuum chamber for a single vacuum test. The primary interest was the performance of the stepper motors and stepper motor drivers in an airless environment. With the vacuum chamber operating at full capacity, the minimum pressure reached 6.5 millitorr. At 1 hour into the test, the axes of the launcher were actuated successfully. At the conclusion of the test, the communication between the 2 microcontrollers on the launcher was tested successfully. Upon removal from the chamber and following a thorough inspection, no defects were found in any of the launcher systems. The entire system then went on to perform a complete proof-of-concept demonstration the next day.
To test the launcher subsystem, two different types of simulations were run. First, a static structural simulation was used to determine the maximum stress in the system. The applied force that was used in the model was the force that would be applied by the largest spring we used during physical launch testing. From this model, we were able to determine the max stress points in the design to be the shaft that supports the launch tubes and the base plate that supports the turntable. The second simulation was a random vibration analysis. This simulation was used to determine the maximum stress areas in the launcher design due to vibrations that occur during a launch from Earth. The random vibration values that were used were in accordance with the standards set by the NASA Technical Standards System's General Environmental Verification Standards, or GEVS. All of the simulations we ran on both the launcher and probe subsystems allowed us to perform virtual testing on parts that we were unable to perform physical tests on. These simulations will allow us to verify our design before we proceed to the physical testing needed to advance to TRL-5 and beyond.
The goal of VELOS is to provide a solution for early exploration for the Artemis program and beyond. The Big Idea Challenge 2020 helped launch this vision and has provided the first step toward the goal of reaching the moon. By completing this challenge, VELOS has achieved TRL-4 with significant progress towards TRL-5. In preparation for TRL-5, the team has identified the next steps required and is evaluating environmental testing facilities for quick advancement. To ensure the future development of VELOS, the team is identifying open solicitations, opportunities, and partnerships that will enable VELOS to go to the moon and beyond.
The first goal of NASA's Science Mission Directorate is to discover the secrets of the universe. VELOS achieves this goal by providing a reliable solution for exploring the unknown regions of the lunar surface. VELOS's capability to deploy a payload over a large distance helps enable future science missions under the Payload and Research Investigations of the Surface of the Moon, or PRISM directive, by providing an innovative solution to deploy multiple sensors simultaneously around an area of interest. This system allows scientists to design their number of probes and payloads. VELOS can be designed to deploy everything from cameras and imagers, micro-robotics, or heavy systems payloads. The VELOS system has a wide range of use cases, allowing reliable delivery of important scientific instruments.
VELOS is a reliable system perfectly fit for exploration of the lunar surface. The team can confidently conclude that VELOS does achieve its objectives to 1. Launch various sensor probes into PSRs as far as 100 meters, and 2. Could return all collected data back to the launcher using a dependable mesh network. VELOS can also be viewed as a reliable economic base system that could safely deploy other types of custom payloads and sensors into the moon's PSRs. Our proof of concept video, combined with all collected data from testing, indicates that this versatile prototype could enable missions and achieve goals in other extreme environments, making VELOS worth the further development, investment, and advancement. The future of space science is dependent on the ability to make an observation, as step 1 of the scientific method states. VELOS, the Variable Exploratory Lunar Observation System, is a unique solution that will assist scientists in their mission to make observations and understand space beyond what we already know it as. The future of space exploration will rely on new innovative solutions, and VELOS will be needed to lead the way.